So in this problem, I've got a constant, a higher order, constant coefficient, non-homogeneous differential equation. I'm going to solve this differential equation using the method of undetermined coefficients. And I've actually given the answer here, so if you want to go ahead and try and work the problem yourself and then check your answer, and then if it doesn't come out, watch the video, then that would be a good exercise. So the first thing you have to do when you're solving this type of differential equation, well, we know we want the general solution. So it's going to look like the complementary solution plus the particular solution. Remember, the complementary solution is the solution to the homogeneous differential equation, and then you just need a solution to the non-homogeneous differential equation. So let's get the complementary solution first, and that's going to involve the homogeneous version of this, y double prime minus y is equal to 0. And if we assume our solutions look like e to the m times our variable y is a function of x. So if we assume our solutions look like e to the m times x, and we take derivatives, y prime is going to be m e to the mx, y double prime is going to be m squared e to the mx, and we can plug those into this differential equation in an attempt to find the m's that will yield solutions. So y double prime is m squared e to the mx minus y is e to the mx. So again, I'm trying to solve for m. I can factor out the e to the mx, and I'm going to get m squared minus 1 equals 0. I can divide the e to the mx out by dividing through it on both sides because I know it's not 0. And then I'm going to end up with m minus 1 if I factor times m plus 1 equals 0, which means that m equals 1 and m equals negative 1 are my solutions. And actually that gives me e to the 1 times x and also e to the negative 1 times x as solutions. So since I have a second order differential equation, I need two linearly independent solutions. So e to the x and e to the negative x are actually going to be linearly independent. You could get the Wronskian to check that. So the y complement, the complementary solution, is actually going to look like this. Y sub c is equal to c1 e to the x plus c2 e to the negative x. So that's the first part. The next thing that I need to do is to find a particular solution to the non-homogeneous differential equation. And I'm going to use undetermined coefficients to do that. So step 2 is to determine or find a particular solution yp. Remember we assumed that the yp will look like the non-homogeneous part of the differential equation. So the non-homogeneous part, remember the dE was y prime minus y equals 4 e to the negative x plus 3 e to the 2x. So if I assume my solution looks like this part, it's going to be an undetermined coefficient a times e to the negative x plus some other undetermined coefficient b times e to the 2x. And I need to be really careful here to check and make sure there's no overlap with my particular solution or no redundancy with my particular solution terms and my complementary solution. So if I check this e to the negative x, it's not redundant with e to the x, but it is actually redundant with c2 e to the negative x. So I'm going to have to multiply that first term in my particular solution by x because I have this redundancy with e to the negative x. The second term, e to the 2x, is different from both e to the x and e to the negative x. So I don't need to multiply it by anything because there is no redundancy there. So my particular solution will look something like ax e to the negative x plus b e to the 2x when I account for redundancies. So the next thing I need to do is solve for these unknown coefficients, a and b, by substituting back into the non-homogeneous differential equation, which means I'm going to need to figure out what the second derivative of yp is. So yp prime. Need to use a product rule on this first term. The a doesn't change under differentiation, it's a constant. The derivative of x is 1, and then that's going to be times e to the negative x, plus the a stays the same, x stays the same, and the derivative of the second function, e to the negative x, is negative e to the negative x, plus, and then I need to differentiate b e to the 2x. So using the chain rule, the derivative of e to the 2x is going to be e to the 2x times the derivative of 2x, which is 2. So if I put that 2 out front, I get 2b e to the 2x. I'm going to go ahead and simplify things a little bit for these first two terms. I will factor out an a e to the negative x, and I have left a 1, and then a negative and an x. And that will just make my next derivative a little cleaner, plus 2b e to the 2x. The second derivative, yp double prime. Again, I have to use the product rule because I have a function e to the negative x times another function 1 minus x. Okay, so the a stays the same, and then the derivative of the first function is negative e to the negative x times the second function 1 minus x plus a stays the same, and then I get e to the negative x stays the same, and then the derivative of 1 minus x is negative 1. For this last function, I'm going to get the derivative of 2b isn't changed, but the derivative of e to the 2x is 2 e to the 2x. And then I can, from these first two terms, factor out an a e to the negative x. And I'm left with a negative 1. Actually, that's a negative 1 times 1 minus x. So now what I'm going to actually do is factor out a negative a e to the negative x. That will make my signs a little nicer. Negative a e to the negative x. So this whole first term is factored out. I'm left with a 1 minus x. And then a negative a e to the negative x leaves me with just a 1 plus 2b. Oops, that's going to be 4b e to the 2x. And then I can add these two constants together. So I get a negative a e to the negative x times 2 minus x plus 4b e to the 2x. Okay, so now I need to take actually into the original differential equation and substitute in this y sub p for y and yp double prime, this last line, for y double prime into the non-homogeneous differential equation. So I will do that next. This was b e to the 2x. Okay, the original differential equation was y double prime minus y equals 4 e to the negative x plus 3 e to the 2x. And so if I substitute yp double prime in for y double prime, I am going to get a negative a e to the negative x times 2 minus x plus 4b e to the 2x minus what I get when I plug yp in, and that's going to be ax e to the x plus b e to the 2x. And that all has to equal the expression on the right-hand side. So I'm going to need this room. So on the right-hand side is my 4 e to the negative x plus 3 e to the 2x. Okay, so what I now need to do on the left-hand side is to group functions together that are the same. And once I do that, I will find the same functions on the right and left-hand side and set their coefficients equal to each other. So on the left-hand side, let me go ahead and distribute. I'm going to get a negative 2a e to the negative x, and then a plus ax e to the negative x, plus 4b e to the 2x. Distributing the negative, I get negative ax e to the x minus b e to the 2x. All of that is equal to 4 e to the negative x plus 3 e to the 2x. I'm going to just separate this line from the last one. Okay, on the left-hand side, if I simplify, the ax e to the negative x and the negative ax e to the x are going to cancel. And let me group the functions that are the same. So this is the only term that has the function e to the negative x. So I get a negative 2a e to the negative x. And these other terms involve the function e to the 2x, here and here. So if I group those together, I actually add the coefficients, 4b and negative b, and I get plus 3b e to the 2x, all equal to 4 e to the negative x plus 3 e to the 2x. So next I just set the coefficients of the functions on the left and right hand side equal. So e to the negative x has a negative 2a. That's going to be equal to 4. And the function e to the 2x has a coefficient of 3b unknown, and that is going to have to equal to 3. That's going to give me two equations. Negative 2a equals 4, which gives me that a is negative 2, dividing both sides by negative 2. And I get another equation which says 3b equals 3, which tells me that b has to be 1. So that actually gives me what my particular solution is when I substitute the a and the b in. So I'll go ahead and write the particular solution down now. Remembering that a is negative 2 and b is 1. The particular solution had the form, it was ax e to the negative x plus b e to the 2x. And so it is negative 2x e to the negative x plus e to the 2x is what the particular solution is. The last step is to combine the complementary solution and the particular solution. So we had the complementary solution had been c1 e to the x plus c2 e to the negative x, and then the particular solution is negative 2x e to the negative x plus e to the 2x. And so that is your general solution. It generates all the solutions to that non-homogeneous differential equation. We actually did have a redundancy in there between the guess for the particular and the complementary solution.